Hello folks, this video covers chapter 9 section 7 about products and quotients of complex numbers that are in polar form. Before we get to that, I want to recap a couple of things that I think you need to be able to quickly recall to be very successful in the rest of this chapter and ultimately on your test next week. One of those things being the unit circle. So I'm not going to give you the unit circle on your test. I'm probably going to give you a blank one, but where you're going to go ahead and have to fill in everything. So in this case right here, you don't have to draw the whole unit circle in your notes. I'm mainly going to be focusing on the first quadrant. Because if you can produce the first quadrant, you can go ahead and reproduce the other three based on what you know here. So the first thing I want to do is go ahead and write our coordinate points at every angle in the first quadrant. So it'll be 0, 1 over there at 0. At 90 degrees, it'll be, oh wait, totally messed that up already. At 0, it's going to be 1, 0. And at 90 degrees, it's going to be 0, 1. Okay, the other easy one is the 45 degree, which is square root of 2 over 2. Square root of 2 over 2. And then the other two numbers are square root of 3 over 2 and 1/2. And so for this 30, 60, 90 triangle that you do first, we go further on the x-axis than we do the y-axis. So that's why we do the bigger number along the x-axis first. So that's why we go square root of 3 over 2 to the right, and then only halfway up of 1/2. And then the 60 degree angle is opposite. It'll be 1/2 square root of 3 over 2. Okay, so that we should be pretty comfortable with just from what we've known from chapters past. And being able to recall, like, if you have to compute, okay, what is the cosine of, 11 pi over 6? Well, even though 11 pi over 6 is in the fourth quadrant, if you recall that in quadrant 1, all of your numbers, all of your coordinates obviously are positive, positive. Quadrant 2 is negative, positive. Quadrant 3 is negative, negative. And 4 is positive, negative. Then when you draw your bow ties, so like this one would be pi over 6 and 7 pi over 6 and 5 pi over 6 and 11 pi over 6. All four of those angles will have these same two coordinates, but their signs would change based on the quadrant that it's in. So as quickly as you can recall sine and cosine of a particular angle, it's also going to be very helpful if you can recall the tangent of every single angle on the unit circle. If you remember that tangent is found by computing y over x, which is kind of like rise over run, which could also be written as slope. If you think about it that way, when we divide y over x, some of the obvious easy ones would be here at 0. And I'm writing this very informally for the sake of space, by the way. But the tangent, well, no, I'll write it formally. Okay, so the tangent of 0 is the slope at this point. So y over x, that'll be 0 over 1, which is still just 0. At 90 degrees, my coordinates are backwards. And if I have 1 divided by 0, we know that the tangent of pi over 2 is undefined. The other tangent that's easy is at pi over 4, because it is those two numbers, the y and the x, are the same, and anything divided by itself is 1. Okay, the 30 and 60 degree angles are pi over 6 and pi over 3. When we divide y over x for the pi over 6 one, you end up with 1/2 over square root of 3 over 2, and then you multiply by the reciprocal and rationalize, yada, yada, yada. When you do that, you end up with the tangent. I wonder if I can hear the Friends theme song in the back of this video. If you can, I hope you enjoy it. You get the tangent of pi over 6 is equal to square root of 3 over 3. And then the pi over 3 angle, when you divide square root of 3 over 2 divided by 1/2, you get that the tangent of pi over 3 is just equal to square root of 3. Now, again, if you can generate the first quadrant, then all of the angles that share, it's even some of it kind of goes with the bow tie. All of the angles that or 180 degrees across the unit circle will end up having the same tangent value, the same slope. This yellow line, all of that has a positive slope. In the second and fourth quadrants, they will have the same slopes, except those will be negative. So if we went around the whole unit circle, then 2/3 over here, 120 degrees, that would have the same slope as the 60 degrees, but negative. So that would be negative square root of 3. And it is opposite of 300, which would be negative square root of 3. Well, let me first copy all the ones in the first quadrant. So this one will be positive square root of 3, positive 1, positive square root of 3 over 3. And in the second quadrant, we have negative 1, negative square root of 3 over 3. And again, if you think about slope, these lines go downward like this. So that's why negative square root of 3 matches. 7 pi over 4 will be negative 1. 330 degrees will be negative square root of 3 over 3. So we're not used to writing tangent for each one of them. Well, obviously in this one too, the tangent of that vertical line is undefined, and over here it is 0. But it's going to be helpful if you know these slopes very quickly. It's going to save you from having to do a lot of side work. The next thing I want to review is the difference between our real numbers and our imaginary numbers. Okay, so real numbers that we have discussed so far could be in two forms. We have rectangular numbers, which when we graph that on the rectangular plane, those are just in the form of x comma y. This is very typical of math even before my class. And then at the very first part of this chapter, we learned about polar coordinates, which have the ordered pair r comma theta. Both of these are different forms, but they represent real numbers. And yesterday, we brought in a complex number, which is imaginary. Now, imaginary numbers have different formats. They still can be in rectangular and polar form, but they look a little bit different. In the rectangular form, your imaginary number could be a plus bi, or you might see it as x plus yi, either one of those. And then in polar form, we learned that it could be written as r times cosine theta plus I sine theta, which could be shorthanded if you want to r cis theta. And cis stands for cosine theta, I sine theta. It's just an abbreviation for that. Okay, you need to know the difference between the real number representation and the imaginary complex representation. So remember, sometimes we'll use the word complex for that. Okay, so what this section specifically is talking about if we were to multiply and divide complex numbers that are in polar form. So if we're multiplying, then that's talking about the product. So if we talk about the product, I want you to, oh, what just happened? Okay, I want you to suppose we have two complex polar numbers. Suppose we have two complex polar numbers. And let's multiply those numbers. So the first one, it's going to have this form over here that we just talked about. But since we have two, we need to distinguish between the two. So, okay, we'll say one is r sub 1 times cosine theta sub 1 plus I sine theta sub 1. And I want to multiply it with a second complex polar number. So that one will be r sub 2 times cosine theta sub 2 plus I sine theta sub 2. And this looks kind of complicated. and it's just kind of how to start the problem and how to set it up. But if we actually multiply things just using, you know, what we know about commutative and distributive properties, then we can go ahead and let's put the R1 and R2 out front because everything's just being multiplied. And then with the binomials, cosine theta 1 with cosine theta 2, we're going to go ahead and FOIL those two binomials. So first, outer, inner, last. So if we multiply the first numbers, we get cosine theta 1 times cosine theta 2. That's the first times the first. Times that outer is going to be cosine theta 1 times, well, I'm getting messed up with FOIL first. Yeah, okay, so that'll be times I sine theta 2. And then inner is going to be I sine theta 1 cosine theta 2. And then the last is going to be I squared sine theta 1 sine theta 2. So that looks like a hot mess. But what's going to happen is we can do a couple of different things. If we realize that, if you remember what I squared is, so yesterday we said that I is equal to the square root of negative 1. So then I squared is the square root of negative 1 times the square root of negative 1. And anytime we have a radical times itself, it's just the term that's on the inside. Therefore, I squared can be just rewritten as a negative 1. So if we change that and maybe rearrange a couple things, then we're going to have cosine theta 1, cosine theta 2. We're going to leave that alone. And then we're going to bring in this part. So let me color code things. Okay, so that's the blue. Then I want to bring in this part that we just did, minus sine theta 1, sine theta 2. And I'm going to group those in parentheses. And I want to add to that then both of these terms that are left both have an I in it. So then if I factor out an I and I write what's left, then I'm gonna do this third term first here. And I have sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 1. And you're like, all right, Miss Schwanier, what the heck are you doing? Why are we writing all this stuff? Well, you're like, I didn't make you prove it. I'm just kind of walking you through it. If you pay very close attention to these highlighted parts, cosine theta 1, cosine theta 2 minus sine times sine, and then sine theta cosine theta plus sine theta cosine theta. These are our identities of adding angles. So if we do that and we convert them, then we end up, or substitute that rather, we end up with R1, R2 times this first highlighted segment can be rewritten as the cosine of theta 1 plus theta 2 in parentheses, plus I times, actually we don't need parentheses anymore around the sine. It would be I times sine of theta sub 1 plus theta sub 2. Okay, and this is the big takeaway for the first parts. So there are going to be two formulas for today. This is how to find the product when you multiply two polar complex numbers. Okay, so for example, okay, the question is going to say find the product of 2 times cosine pi over 2 plus I sine pi over 2 times 4 times cosine pi over 3 plus I sine pi over 3. Then write product in rectangular form. So I'll give you a second to write that. Now notice what we have going on here. We have two complex polar numbers. Complex because they involve I. Polar because they have obviously R's and thetas. They have radian angles. So our job is to figure out what each of the variables are. So we're kind of going backwards. So, well, I guess it's not really going backwards yet. If we go forward, we started off with this here, we're going to do exactly the same thing as we did earlier, except instead of going through the derivation of it, you can skip straight to the equation. R1 times R2 times all the stuff in between. So let's identify what those things are. Well, it starts off with R1. Each complex number starts off with R. So if that one's R1, this will be R2. And then the thetas, the angles in between, pi over 2 will be considered theta 1, and pi over 3 will be considered theta sub 2. So then if we have these variables, then we're going to be plugging those into this product form. So when we do that, we're going to get 2 times 4 times the cosine of theta sub 1 plus theta sub 2. So that for us is going to be pi over 2 plus pi over 3 plus I times the sine of pi over 2 plus pi over 3. So all I did was substitute in the values for r's and thetas into the equation. And then your goal from here is just to go ahead and simplify the pi over 2 plus pi over 3. And you can't use your calculator because your calculator is not going to understand the pi unless you calculate it without it. So you'll kind of have to go back to pen and paper, oh such a tragedy, to add these fractions. Well, rule for adding fractions is we have to have common denominators. The LCD among 2 and 3 is 6. So if we multiply this first fraction by 3 over 3 and the second fraction by 2 over 2, then we end up with the fractions 3 pi over 6 plus 2 pi over 6. And now that we have common denominators, we can add our numerators. So 3 pi plus 2 pi, you treat pi like a variable. That's considered 5 pi over 6. So then we're going to simplify that. And we're also going to simplify 2 times 4. So that's going to be 8 times the cosine of, remember this is now 5 pi over 6, plus I times the sine of 5 pi over 6. So this is the first part. This is the first answer. That is the product of the two polar numbers. Now, it's still just in polar form. So if I want you to convert it to rectangular form, then literally we're just going to like simplify these values. And maybe you need to write yourself a note to do that. To put in rectangular, literally simplify values. Meaning, look at your unit circle and figure out, okay, where is cosine of 5 pi over 6? Where is 5 pi over 6? And at that point, where is the cosine and the sine? So if we reference our unit circle up top, 5 pi over 6 is going to be over here, this highlighted green angle. Which if you use your bow tie, that's going to have the same coordinates as this 30-degree angle, except they're going to be, the x-coordinate's going to be opposite. So the x-coordinate is going to be negative square root of 3 over 2. So maybe let me write that part first. That 5 pi over 6 has coordinates negative square root of 3 over 2, and then a y-coordinate of 1/2. So then when we substitute these values into the previous answer, then we get 8 times, instead of cosine of 5 pi over 6, cosine is the x term. So it's going to be negative square root of 3 over 2. Well, I shouldn't close that yet. Plus I times the sine is the y value, which is 1/2. And then again, we can go ahead and distribute this 8 to both terms. And then we get negative 8 square root of 3 over 2 plus 8I times 1/2. And then if we simplify one more time, 8 divided by 2, or negative 8 divided by 2 is negative 4 square roots of 3 plus 8 times 1/2 will be 4I. So this is your answer of the product in polar form. And this is the product in rectangular form. And of course, after the product, then we took quotients, which is instead of multiplying our polar complex numbers, we will divide them. Now, I'm not going to take you through the derivation for time purposes, so just trust me on this one. It uses similar tactics, though, of the trig identities that we've already learned. So quotient means divide. So I'm going to take one polar complex number. So it'll be r sub 1 times cosine theta sub 1 plus I sine theta sub 1 divided by r sub 2 over cosine theta sub 2 plus I sine theta sub 2. Okay, when you divide these numbers, your answer can be written as r1 divided by r2 times the cosine of theta 1 minus theta sub 2 plus I times sine of theta sub 1 minus theta sub 2. So again, it also uses the difference identity. So this is the second big takeaway. The first one was the product formula. This one is the quotient formula. So this will be our second and final example. Directions, I want you to find the quotient of 21, open parentheses, times the cosine of 7 pi over 6 plus I times the sine of 7 pi over 6 divided by 7 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. Then express your quotients in rectangular form. And of course, feel free to abbreviate some of this stuff. Okay, to find the quotient, we're going to follow the rules given in this highlighted pink formula. So again, if we identify that 21 is r sub 1, theta sub 1 is 7 pi over 6, and then in our second coordinate, 7 is r sub 2, and theta sub 2 is 4 pi over 3, then we can fill in the right side of the equation. So r sub 1 over r sub 2 is going to be 21 over 7, excuse me, times the cosine of theta sub 1 minus theta sub 2. So that'll be 7 pi over 6 minus 4 pi over 3 plus I times the sine of 7 pi over 6 minus 4 pi over 3. And again, you'll need to go off to the side in order to figure out how to subtract these fractions. So if I've got 7 pi over 6 minus 4 pi over 3, I've got to have common denominators. So if I multiply the second fraction by 2 over 2, then I have 7 pi over 6 minus 8 pi over 6. And then since I have common denominators of 6, I can subtract the numerator. 7 pi minus 8 pi is negative 1 pi, which will just be negative pi over 6. So then what that means is we can go ahead and rewrite our quotient. 21 divided by 7 is 3, times the cosine of negative pi over 6 plus I times the sine of negative pi over 6. So again, that is the quotient. That is step 1. The second part is expressing your quotient in rectangular form. So just like we did in the last question, in order to put in rectangular form, we literally need to just simplify this stuff. So if I'm going to do that, I'm going to get negative, or sorry, I don't know why I said negative, 3 times the cosine of negative pi over 6. So negative pi over 6, if you add 2 pi to that, or if you just use your logic on the unit circle, negative pi over 6 is going to be the same thing as a positive 11 pi over 6. So you're going to use those two coordinates, except your y value is going to be negative. So if we do that, oh, things moved. I moved it a few times. I wonder if I just lost everything that I wrote down here. Oh, there we go. Okay, sweet. Okay, so then if I use my coordinates at negative pi over 6, which have square root of 3 over 2, negative 1/2, and then I plug those in for cosine and sine. So it'd be negative 3 times the cosine of negative 5 pi, or negative pi over 6 will be square root of 3 over 2, plus I times the sine is the y value, which will be negative 1/2. And then if we distribute this 3 into both numbers, then that's going to be 3 square root of 3 over 2 plus 3i times negative 1/2, which then this is going to equal 3 square root of 3 over 2 plus 3i times negative 1/2 is the same thing as, I can go ahead and switch this plus sign to negative 3/2 I. Now, technically, negative 3/2 I can be the same thing as 3 over I squared, but if it's going to have the form a plus bi, typically we go ahead and isolate that real part, or that real coefficient of I. I don't accept either one of those. So this part is how you find the quotient, and then once you find the quotient, how to convert it to the rectangular version of that number.